For decades, the aviation industry has been dominated by a handful of nations, with the United States leading the charge in pushing the boundaries of what's possible in the skies. But in December 2020, an announcement from China sent shockwaves through the global aerospace community, challenging long-held assumptions about technological supremacy and the future of flight itself. China revealed that it was actively developing a revolutionary propulsion system, an oblique detonation ramjet engine capable of propelling aircraft at speeds reaching Mach 16. To put that into perspective, this means an aircraft could theoretically circumnavigate our entire planet in approximately 2 hours. That's faster than most people's morning commute, yet covering a distance of roughly 40,000 kilometers. To understand the magnitude of this claim, consider that the fastest operational aircraft ever built, the experimental vehicles that have pushed the very limits of aerodynamics and materials science, have only managed to reach speeds around Mach 9.8. China's announcement wasn't just about incremental progress. It represented a potential leap forward that could fundamentally reshape how we think about global transportation, military strategy, and international commerce. This development didn't emerge in a vacuum. It's the culmination of decades of determined effort, strategic investment, and perhaps most importantly, a response to significant external pressure. Western sanctions, designed to slow China's technological advancement in sensitive sectors, may have inadvertently accelerated the very innovation they sought to contain. Today, we're going to explore this remarkable story in depth. We'll examine the historical context that led to this moment, the science behind this revolutionary engine, what makes it so dramatically different from existing technology, and what its existence might mean for the future of global aviation and geopolitical power dynamics. If you appreciate in-depth analysis of technological breakthroughs that are shaping our world, please consider subscribing to this channel. Your support helps us continue producing content that goes beyond headlines to explore the stories that truly matter. Now let's begin our journey into the cutting edge of aerospace engineering. To understand China's current position in aerospace technology, we need to rewind the clock to the late 1950s. During this period, China's leadership made a strategic decision that would shape the nation's trajectory for generations to come. They committed to building a robust domestic aviation industry. This wasn't merely about national pride or prestige. In the post-World War II era, aviation technology had become synonymous with industrial capacity, military power, and economic vitality. Nations that controlled the skies held significant advantages in virtually every domain, from commerce to defense. However, China's ambitions in this sector quickly became a source of concern for established aerospace powers, particularly the United States and its allies. As China's capabilities began to develop through the latter decades of the 20th century, Western nations implemented increasingly stringent measures designed to limit technology transfer and slow progress. The United States took particularly aggressive action, placing numerous Chinese aviation companies on what's known as the Entity List, effectively a military blacklist that restricts these organizations from acquiring American technology, components, or expertise. This wasn't limited to complete systems. The restrictions extended to critical subsystems and components that form the backbone of modern aerospace engineering. High-performance sensors that allow aircraft to perceive their environment, advanced laser systems used for everything from targeting to communications, sophisticated avionics that serve as the brains of modern aircraft, and precision navigation equipment. All of these became difficult or impossible for Chinese companies to obtain through legitimate channels. But the restrictions went even deeper. The United States coordinated with allies, including Japan and South Korea, to implement comprehensive export controls on advanced semiconductors and microelectronics. These components are absolutely essential for modern aerospace systems, controlling everything from engine performance to flight dynamics. Think of it this way. Trying to build a 21st century aircraft without access to cutting-edge chips is like trying to build a smartphone using 1990s technology. It's theoretically possible, but the resulting product will be fundamentally limited in performance and capability. For many nations, such comprehensive sanctions might have proven insurmountable. The temptation to abandon domestic development in favor of purchasing foreign systems or to simply accept technological inferiority must have been significant. But China chose a different path. Rather than viewing these restrictions as insurmountable obstacles, Chinese policymakers and engineers saw them as a challenge to overcome, and perhaps even as an opportunity. The sanctions created a powerful incentive for domestic innovation, forcing Chinese researchers to develop indigenous solutions rather than relying on foreign technology. China's journey toward aerospace self-sufficiency began with modest but significant steps. In 1983, Chinese engineers announced the successful development of the turbojet 14 engine. By today's standards, this engine was, honestly, relatively unsophisticated. Its performance characteristics were far behind contemporary Western designs, and, well, its reliability left room for improvement. But its importance wasn't measured in performance specifications alone. The turbojet 14 represented something far more valuable: proof that China could design, manufacture, and test a functioning jet engine using primarily domestic resources and expertise. It was a foundation upon which more sophisticated systems could be built. The engine found its primary application in the J-8 fighter series, specifically the H, F, and G variants. These aircraft served as test beds and operational platforms that allowed Chinese engineers to gain real-world experience with jet propulsion systems. Every hour of operation, every maintenance cycle, and every performance evaluation provided data and insights that informed future designs. Throughout the 1980s and 1990s, China's aerospace sector expanded rapidly, but often remained in the shadow of Western and Russian capabilities. Progress was steady but, incremental. Engineers learned from both successes and failures, gradually building the institutional knowledge and manufacturing capabilities necessary for more ambitious projects. By the early 2000s, this accumulated experience began to yield more impressive results. Chinese researchers unveiled the Turbofan 15 engine, a far more sophisticated design that incorporated lessons learned over 2 decades of development. The Turbofan 15 represented a qualitative leap forward in several key areas. It utilized advanced high-temperature alloys, materials that could withstand the extreme thermal and mechanical stresses inside a modern jet engine without degrading or failing. These alloys are notoriously difficult to develop and manufacture, requiring precise control over metallurgical processes and strict quality standards. The engine also featured significantly improved combustion efficiency, meaning it could extract more useful work from each kilogram of fuel consumed. This translated directly into improved range, higher speeds, or greater payload capacity, all critical performance parameters for military and civilian aircraft alike. Perhaps most importantly, the Turbofan 15 delivered substantially greater thrust than previous Chinese designs. This made it suitable for powering China's fifth-generation fighter aircraft, the J-20, which required engines capable of sustained supersonic flight and exceptional maneuverability. The J-20's debut represented a symbolic moment for Chinese aerospace. Here was an aircraft that could stand comparison with the most advanced fighters in the world, powered by domestically developed engines. It was tangible evidence that decades of investment and determination were paying dividends. But even as the Turbofan 15 entered service, Chinese researchers were already pushing toward the next frontier. They weren't content with merely matching existing Western capabilities. They wanted to leapfrog them entirely. To understand why China's December 2020 announcement was so significant, we need to appreciate the enormous technical challenges involved in hypersonic flight. That is, flight at speeds exceeding Mach 5, or 5 times the speed of sound. At these velocities, the physics of flight changes dramatically. The air itself becomes less like a fluid to be smoothly displaced and more like a series of violent collisions. The compression of air molecules ahead of the vehicle generates enormous heat. temperatures that can exceed those found on the surface of the sun. Materials that perform perfectly well at subsonic or even supersonic speeds can melt, ablate, or structurally fail within seconds at hypersonic velocities. The challenge isn't simply making something go fast. It's making something that can survive going fast long enough to be useful. Engine design becomes particularly problematic at these speeds. Traditional jet engines, which work by compressing incoming air, mixing it with fuel, combusting the mixture, and expelling it at high velocity, face fundamental limitations. At hypersonic speeds, the air entering the engine is already moving so fast and is so hot that conventional compression and combustion processes become inefficient or impossible. The United States, despite its vast aerospace expertise and decades of research funding, has struggled to develop practical hypersonic propulsion systems. Various experimental programs have demonstrated limited success, but sustained controlled hypersonic flight has remained frustratingly elusive. In July 2020, an American company called Boom Supersonic made headlines with the XB-1, a demonstrator aircraft for a planned supersonic passenger plane. The XB-1 utilized three J8515 engines manufactured by General Electric, each providing approximately 12,000 pounds of thrust. This configuration was designed to push the aircraft to speeds around Mach 2.2. At this velocity, the XB-1 could complete a transatlantic crossing from New York to London in roughly 3 hours and 15 minutes. Roughly half the time required by a conventional airliner. This represented genuine progress in supersonic civilian aviation, a field that had been dormant since the retirement of the Concorde in 2003. The announcement generated considerable excitement in the aerospace community. Here was evidence that commercial supersonic flight might finally be making a comeback, potentially opening a new era of rapid global travel for those who could afford premium tickets. But just months later, China's announcement made Boom Supersonic's achievement seem almost pedestrian by comparison. A top speed of Mach 2.2 is impressive, but Mach 16 is transformative. We're not talking about cutting flight times in half. We're talking about reducing intercontinental journeys from hours to minutes. Detonation, a new way to burn. So, what exactly is an oblique detonation ramjet engine, and why does it promise such revolutionary performance? At its core, this technology involves a fundamentally different approach to combustion, the process by which chemical energy stored in fuel is converted into the kinetic energy that propels an aircraft forward. In conventional jet engines, combustion occurs through what engineers call deflagration. Fuel is mixed with air and ignited, and the resulting flame front moves through the mixture at subsonic speeds, typically just a few meters per second. The heat released causes the combustion products to expand, generating pressure that ultimately produces thrust. This process works well at moderate speeds, but it has inherent efficiency limitations. A significant portion of the fuel's chemical energy is wasted as heat rather than being converted into useful propulsion. Detonation combustion represents a radically different approach. Instead of a relatively slow-moving flame front, detonation produces a supersonic shock wave that propagates through the fuel-air mixture. Behind this shock wave, combustion occurs almost instantaneously. The difference is dramatic. Detonation can release more than 70% of the fuel's available energy in an extraordinarily small volume and time frame. The thermal efficiency is more than double that of conventional deflagration-based combustion. This means more thrust from the same amount of fuel, or, alternatively, the same thrust with far less fuel consumption. But harnessing detonation for propulsion has proven extremely difficult. Detonations are inherently unstable and difficult to control. Creating the conditions for sustained, stable detonation combustion while managing the extreme temperatures and pressures involved requires solving problems that have challenged researchers for decades. The oblique aspect of China's design refers to the geometry of the detonation wave relative to the incoming airflow. Rather than attempting to create a perpendicular detonation wave, which creates tremendous structural stresses and control challenges, the oblique design allows the detonation to occur at an angle. This makes it somewhat easier to stabilize and control while still capturing most of the efficiency benefits. According to available information, Chinese engineers have developed a novel approach to fuel injection that differs fundamentally from previous designs. Rather than attempting to mix fuel with the incoming supersonic airstream inside the engine intake, a process fraught with difficulty, fuel is pre-injected on the engine surface. The resulting combustible mixture is then drawn into the combustion chamber through carefully designed shockwave patterns that also serve to initiate the detonation process. This approach addresses several problems that have plagued previous hypersonic engine designs. It reduces the excessive fuel consumption that often occurs when trying to mix and burn fuel in a supersonic airstream. It minimizes destructive vibrations that can damage engine components or even the entire vehicle structure. And it provides more stable, controllable combustion across a wider range of operating conditions. Furthermore, Chinese researchers have optimized the shock wave patterns within the engine to maximize detonation efficiency. These shock waves serve multiple purposes. They compress and heat the incoming air, help mix the fuel, initiate the detonation, and shape the resulting combustion products to maximize thrust. The cumulative effect of these innovations is an engine that can operate efficiently at speeds that would cause traditional engines to fail or perform poorly. Early testing suggests this design can maintain stable operation while propelling aircraft at velocities up to Mach 16, a speed that seems almost incomprehensible. Testing the impossible. Developing an engine capable of Mach 16 flight is one thing. Actually testing it presents an entirely different set of challenges. You can't simply attach an experimental hypersonic engine to an aircraft and hope for the best. The consequences of failure at those speeds would be catastrophic, and even if the engine performed flawlessly, the aircraft itself would need to survive conditions unlike anything experienced in conventional flight. This is where wind tunnels become essential. These facilities allow engineers to simulate flight conditions in a controlled environment, where sensors can gather data and high-speed cameras can capture every detail of an engine's operation. For decades, the most advanced hypersonic wind tunnel in existence was the X-15 facility constructed by NASA during the 1960s. This impressive installation, built during the height of the space race, could simulate flight conditions at speeds up to 15 times the speed of sound. It played a crucial role in developing vehicles and engines for early hypersonic research. But even this facility, representing some of the most advanced aerospace testing infrastructure ever built, proved inadequate for testing China's oblique detonation ramjet. An engine designed to operate at Mach 16 needs to be tested at speeds even higher than its operational velocity to ensure it has adequate performance margins and to understand its behavior under extreme conditions. China's response to this challenge was characteristically ambitious. They built an entirely new facility from the ground up. The JF-22 hypersonic wind tunnel, developed by Chinese researchers and engineers, represents the current state-of-the-art in aerospace testing infrastructure. The JF-22's capabilities are staggering. It can simulate flight conditions at approximately 30 times the speed of sound, Mach 30. At this velocity, air molecules have so much kinetic energy that they begin to dissociate, breaking apart into individual atoms. The temperatures involved exceed 10,000 degrees Celsius. Materials sublimate directly from solid to vapor. We're operating in conditions more commonly associated with atmospheric re-entry from space than with atmospheric flight. Building a facility capable of generating and sustaining these conditions, even for brief periods, required solving numerous engineering challenges. The power requirements alone are immense. The structural stresses on the tunnel itself must be carefully managed, and instruments capable of gathering meaningful data in such an extreme environment must be carefully designed and precisely calibrated. but the investment has paid off. Initial testing of the oblique detonation ramjet engine in the JF-22 facility has reportedly demonstrated performance that meets or exceeds design specifications. The engine has shown stable operation at speeds up to Mach 16, validating the fundamental design concepts and proving that the various innovations incorporated into the engine work as intended. To put this achievement in context, consider that the American aerospace industry has spent decades and billions of dollars pursuing hypersonic propulsion technology. Programs like the X-43 and X-51 have demonstrated brief periods of hypersonic flight, but nothing approaching the sustained, stable performance that China's new engine apparently achieves. The X-43A, during a 2004 test flight, briefly reached 7 times the speed of sound. But the scramjet engine operated in optimal conditions for only 11 seconds, hardly long enough to be useful for any practical application. It was a proof of concept, demonstrating that scramjet technology could work, but also revealing how far researchers were from making it practical. The X-51A program, launched nearly a decade later, showed incremental progress. In a 2013 test, the vehicle accelerated from Mach 4.8 to Mach 5.1 and maintained hypersonic flight for approximately 6 minutes. This was far more impressive than the X-43's brief demonstration, but it still highlighted the enormous gap between laboratory demonstrations and operational systems. In contrast, China's oblique detonation ramjet reportedly operates stably across a much wider speed range and has shown sustained performance in testing. If these reports are accurate, and there's no particular reason to doubt them, given China's track record of technological achievement, then Chinese researchers have solved problems that have stymied American engineers for years. From weakness to strength. The irony of this situation is not lost on observers of global aerospace dynamics. For decades, engine technology was widely considered one of the weakest links in China's aviation industry. Whether building military fighters or civilian airliners, Chinese manufacturers consistently struggled to develop engines that matched the performance, reliability, and efficiency of Western designs. This wasn't due to lack of effort or investment. China poured resources into engine development programs and recruited talented engineers and researchers. But jet engine design is one of the most demanding disciplines in all of engineering, requiring expertise across multiple domains, including thermodynamics, fluid mechanics, materials science, manufacturing, and control systems. The accumulated institutional knowledge held by companies like General Electric, Pratt & Whitney, and Rolls-Royce, built up over decades of continuous development, proved difficult to replicate. Western sanctions made it harder still, cutting off access to advanced materials, manufacturing equipment, and design tools that could have accelerated Chinese progress. Many analysts predicted that this technological gap would persist for decades. Some suggested China might never truly catch up, that the combination of technical complexity and restricted access to foreign technology would permanently limit Chinese engine capabilities. The oblique detonation ramjet project demonstrates how wrong such predictions can be. Rather than attempting to replicate existing Western technology, a strategy that would always leave China playing catch-up, Chinese researchers pursued a fundamentally different approach. This strategy of pursuing alternative technological pathways when conventional routes are blocked has become a hallmark of Chinese innovation in recent years. Unable to access the latest Western chips, Chinese companies have invested heavily in alternative computing architectures. Blocked from certain satellite technologies, China has developed its own global navigation system. Restricted in access to advanced manufacturing equipment, Chinese firms have built their own semiconductor fabrication tools. The oblique detonation ramjet follows this pattern. By exploring combustion physics and engine architectures that Western researchers had largely neglected, Chinese engineers found a path forward that didn't require access to Western technology or expertise. The result is an engine design that may actually represent a generational leap beyond current Western capabilities. Global implications. The potential implications of China's hypersonic engine development extend far beyond aerospace engineering circles. If this technology transitions from laboratory demonstrations to operational systems, admittedly still a significant if, it could reshape multiple domains simultaneously. From a military perspective, hypersonic weapons and platforms have been a focus of intense interest among major powers for years. The ability to strike targets anywhere on Earth within 2 hours, coupled with the extreme difficulty of detecting and intercepting vehicles traveling at such speeds, would represent a fundamental shift in strategic calculations. Current missile defense systems are designed primarily to intercept ballistic missiles, which follow predictable trajectories and can be tracked throughout their flight. A hypersonic vehicle, maneuvering at Mach 16 within the atmosphere, presents an entirely different challenge. Detection windows are measured in seconds rather than minutes. Interception geometry becomes far more complex. And the sheer kinetic energy of such a vehicle means that even without explosives, the impact alone would be devastating. Beyond military applications, hypersonic propulsion could revolutionize global transportation. Imagine boarding a commercial flight in Beijing and stepping off in New York 2 hours later, or traveling from London to Sydney in the time it currently takes to fly from London to Frankfurt.